And he is from VMware. He's a staff engineer over there and is working on high-performance I/O device virtualization for more than a decade. His focus is on high bandwidth, low latency communication, and he's been involved in the design and implementation of VMCI device and the paravirtual RDMA device. It's my pleasure to invite Jorgen to talk about supporting live migration of VMs on RDMA with RDMA endpoints. So there you go. Jorgen, can we? Yeah, there you go. We can hear you now.
All right, thank you. Yeah, I'm presenting the work here on supporting live migration of VMs communicating with bare metal RDMA endpoints. And this is work done by the PV RDMA team at VMware. So most of the members, or all of the members, current members are listed here. Next slide, please. So we'll start out with a brief overview of the VMware paravirtual RDMA device, PV RDMA as it's called, and then look at how we currently support live migration for virtualized endpoints, and then move on to looking into the issues and how to support bare metal endpoints communicating with VMs that do live migration. And we'll finish off with an example of such a bare metal endpoint and then conclude. Next slide, please. So PV RDMA is inside the VM, it's exposed as a virtual PCIe device. It has its own set of drivers and libraries hooking into the RDMA stack of the guest OS. Each PV RDMA device exposes to the virtual machine or the guest a virtual RDMA resource space. So each VM has a picture or has the concept of a dedicated RDMA device that it can use for RDMA communication. Underneath in the hypervisor, we map these virtual devices onto physical RDMA resources, and currently this is Rocky-based RDMA only. So all the virtual resources created by a guest will be mapped to a physical resource on the physical HCA. And so in this way, a group of VMs can share a single HCA on the host while still having the impression that they are the sole user of an RDMA device. So next slide, please. So moving on to how we deal with vMotion in the fully virtualized case. So to vMotion a VM, we need to capture the state of the PV RDMA device in a consistent way so that we can resume communication on a destination host with the peers of the VM without disrupting the RDMA communication of the virtual machine. So in our case, during normal operation, the state will be sort of spread out between the device simulation layer in software and the state on the physical HCA, where you have the protocol regarding, controlling the exchange of operations between the peers. And so to bring it into a consistent state, since we only have limited visibility into the state of the HCA, we have a distributed coordination protocol that when we do vMotion, we first have all the vMotioning VM and its peers drain the send queue of the devices so that there are no in-flight communication between the VM and the vMotioning VM and its peers. At that point, we then extract the remaining state information from the HCA using regular query verbs to get the PSNs and so on, and then capture the state in a snapshot for the VM. When we move the VM, while we're moving the VM, the peers of the VM will pause all traffic to that particular vMotioning VM, but can still talk to other VMs that are operational. Next slide, please. So on the destination host, we then use this snapshot of the VM to recreate the state of the PV-RDMA device. And as part of that, we then recreate all the physical resources of the PV-RDMA device as well. First on the for the vMotion VM, and then having set up all the connection state on the local HCA, we again use a distributed coordination protocol to make all the peer VMs similarly restore the state, connection state on their HCAs. When they acknowledge back to the vMotion VM that everything is set up, communication is resumed between the endpoints, and of course also for the VMs that would not have noticed anything except for some wall clock downtime for the VMs. Next slide, please. So, as mentioned, we recreate resources following a vMotion. So this means that the resource IDs of the physical resources will change. And so here we have a picture of showing the VM before and after vMotion. And in the backend, we have these maps between the virtual resource IDs and the physical resource IDs. And during vMotion, following a vMotion, the virtual resource ID must remain the same, since those are the ones that are used by the applications inside the guest that are not aware of anything like any migration or anything. But the local, the maps in the backend needs to be updated. So here, for example, we allocate a new queue pair on the destination, and that might not have the same resource as the queue pair number as on the source. So we need to register that updated translation, and in effect also notify peers of the VM that when they use a specific queue pair number inside the VM, it needs now to be translated to a different physical queue pair number. And this is in the virtual environment. So moving on to bare metal, things get a little bit both simpler and more complicated. Next slide, please. And next slide. So when communicating with bare metal endpoints, they of course only have one set of resource IDs. The physical resource IDs are the ones that are exposed to the application or UOPs inside the bare metal endpoint. And when a VM communicates with such a bare metal endpoint, any connection setup state that is exchanged at application or level will refer to the physical resources. So now the VM has to use the physical resource IDs as well. And so what we're doing then in the presence of bare metal endpoints is that instead of having a mapping, we have basically, well, it's an identity map. We allocate resources on the physical HCA and expose those physical resource IDs directly to the VM. And so in this case, it's fine. They can now communicate. But of course, following a vMotion, we have some challenges, since we're not really sure. We're not guaranteed that we can recreate resources with the same resource IDs on a different host, since we just saw they could change. But without vMotion, without supporting vMotion, this is the support for bare metal endpoints that we introduced in ESXi 70U1 for PV-RDMA. Next slide, please. When looking at supporting live migration for bare metal endpoints, we have some challenges. As mentioned earlier, we have this coordination protocol to ensure this consistent queue pair state, and bare metal endpoints, well, they don't really know, they don't support that. We don't have any control over them. So PV-RDMA can still stop outgoing operations, yeah, but the bare metal endpoints are outside our control. A second challenge is that for the VMware and vMotion, so our version of live migration, we use a pre-copy phase where memory is transferred while the VM is still active, and to ensure that any data that has been modified by the VM or by I/O devices is correctly transferred, we need the notifications when guest memory is updated by the hardware devices. And for the fully virtualized case, we have actually a protocol that takes care of that for the RDMA traffic. But again, this is not really possible for the bare metal case. And finally, as briefly touched upon earlier, since multiple VMs may share the HCA, there's no way we can guarantee that a new resource can be created with the same resource ID when we restore the PV-RDMA state on the destination ESX host, since other VMs could have been handed out the same QPN or R key for an MR or so on. So in sorry, next slide, please. So in collaboration with our hardware partners, we have identified 3 areas of hardware support that will enable live migration for bare metal endpoints. So first, the RDMA namespaces, where we allow, where the hardware supports sort of isolated resource ID namespaces so that we can have 2 VMs operating in 2 different namespaces and where they can freely allocate resource identifiers without concern of existing, or I mean, without concern for interference from others. Secondly, hardware-assisted suspend resume support, so that we can pause and resume processing of a queue pair on the HCA, and also retrieve sort of the runtime state of the queue pair on the HCA and update the state of a queue pair on the HCA. And finally, support for tracking accesses to guest memory during during the pre-copy phase. All right.
Yeah. Okay, there is a question from Christoph. Christoph, do you want to ask your questions? I think there are a couple of them here.
Well, I just noted that there is an InfiniBand function to actually reassign the resources that we want. You can send a special track to the application, and it should be doing that.
All right. Okay. Yeah. So that's we haven't looked into that possibility. So thanks for providing that. Okay. Next slide, please. So the first piece of support is the RDMA namespaces. So basically, the HCA now supports the ability to create multiple namespaces, each identified with a MAC and a VLAN. And within that namespace, it's possible to allocate a full range of resource IDs. And so we use that to assign a namespace per VM. So we no longer need to have the mapping. We can just have the same resource IDs for the physical and virtual resource IDs. And so there's no longer a need for translations. And so on vMotion, what we would do is when in the virtualized cases, well, in any in any kind of vMotion case or live migration case, we would, on the destination VM, we create a namespace for the VM when we move there, and then we recreate all the Q pairs and MRs with the same resource IDs that they had on the source. And so this removes some of this bookkeeping information that we talked about earlier, the translations that that the VMs and their peers needs to be aware of. And so this has a positive effect both on the vMotion time itself, but also on the scalability of PV-RDMA. And I'll come back to the scalability on the next slide. But this support was introduced in ESXi 7.0 and was developed in collaboration with our hardware partners NVIDIA, Mellanox, and Marvell. Next slide, please. So on the scalability aspects of namespaces, so before we had the namespaces, whenever we had a virtual to physical mapping that could be used by the peer VMs, we would need to distribute this mapping in some way. So certain applications that create a lot of resources continuously through the runtime of the application, we would actually see a huge performance impact when distributing these mappings. And with namespaces, so we no longer have a need for distributing any mappings, and these kinds of applications saw a significant performance improvement. So even without looking at migration itself, just having the namespaces simplify the way we deal with the resources in virtual and physical. Next slide, please. Moving on to the second piece of the puzzle, the hardware-assisted suspend resume support. We introduced 4 new operations. So suspending a Q pair, so just pausing the execution of the Q pair on the HCA, then querying the Q pair for the runtime state. So when you already have query operations on Q pairs, but this is extracting more details about the in-flight operations of the Q pair, and then an operation to create a Q pair in the suspended state given runtime state. So this essentially recreates a Q pair that was suspended in a similar state. And then finally, we have an operation to resume the Q pair again. And this can be used either with the suspended Q pair or, well, a Q pair that was suspended using the suspend call, or a Q pair that was created as a suspended Q pair. And so while the Q pairs are suspended, it's possible for the HCA to reply to incoming requests from the peers with RNX as to not cause any connection termination. Well, alternatives could be to adjust some of the retry timeouts and so on. So the actual runtime state is based on the InfiniBand spec. A goal was to make it vendor neutral so that we have the ability to vMotion even between different hardware vendors. And it essentially captures state about the currently executing rookies and also incoming RDMA writes and outgoing RDMA read operations, as well as recently processed atomic operations. And these APIs and this state has been developed again with our hardware partners NVIDIA, Mellanox, and Marvell, and is actually available now in ESXi 7.0 U2 that was released after the deadline for the slides. So We can now say, well, it's supported, hardware assisted suspend resume is supported for Marvell adapters in the most recent release of ESX i7.0, which is update release 2. Next slide, please. So looking at in more detail on how we capture the state, we have on the right-hand side, we have a diagram showing at the top the virtual state of a queue pair with the send and receive queues, the work requests in the send and receive queues, the MRs and completion queues. And we see those are mapped to actual physical resources at the bottom, where there's some difference in state in that we have work requests that are currently executing, and it's sort of indicated by the red part of those wookies. So in the virtual state, we only update the send queues and receive queues when we get a completion from the physical queue pair. So, but other than that, we have the complete we have a complete picture of the state of the queue pair. So when we need to capture the state now, we suspend the physical queue pair. We poll the completion queues, the physical completion queues, to remove any completed work requests from the virtual state. And at this point, there should be a direct match between the send and receive queues on the physical and the virtual QP. We then capture the state of the physical queue pair and store that together with the complete virtual state. And the physical, so the runtime state of the queue pair is mainly sort of the sequence numbers, the things that I mentioned on the previous slides. It doesn't capture, we don't need to capture the work queue elements, the wookies themselves, since we already have, we're already tracking that as part of the virtual state. Next slide, please. So having captured the state and transferred it to the destination host, we then start by restoring the virtual state. We recreate all the RDMA resources required by the queue pair, so protection domains, completion queues, memory regions, and so on. And then we create the suspended queue pair referring to these new physical resources and with the runtime state retrieved from on the source host. At this point, we still have empty send and receive queues, since those were not part of the captured state, and we will then use regular posts to repopulate the send and receive queues with the wookies in the same order and the numbers as on the source host, and then we can resume the processing of the queue pair.
I will, I'm guessing you're looking at questions, so I can bring it up those now if you want.
No, I think maybe I'll just, we're almost, maybe it's easier to take it at the end, or
okay.
collect that at the end. So let me just see. Yeah, so this is sort of concludes the hardware assisted suspend resume of the. Right, this concludes the hardware suspended hardware assisted resume, and so we have next slide, please. And so the final puzzle piece of the puzzle is handling the pre-copying of the virtual machine state. And so, as we briefly discussed earlier, we have this pre-copy phase where we try to move memory while this VM is still active, and we need to know if guest memory is changing. And so for RDMA, the challenge is mainly the incoming RDMA writes that may go directly to virtual machine memory or host memory without any notification to the host. So to get around that, in ESXi, we introduced a new set of APIs that allows us to work with the HCAs to collect the write traces. So the HCAs themselves will collect write traces during the pre-copy phase. There's an activate and deactivate of the write tracing. And then you can get notifications and you can be polling for these traces to collect them during this pre-copy phase. And we can use that to notify the hypervisor of any data that needs to, any virtual machine memory that needs to be retransmitted. So the actual write traces can be kind of flexible in how fine-grained the tracing needs to be. It could be page size, or it could even be larger than a page size, depending on sort of a trade-off between how much information you want to store compared to the number of actual incoming RDMA writes. And this is also part of the newly released ESXi 7.0 U2, again, for the Marvell adapters. So this was developed in collaboration with Marvell. And so in that sense, for ESXi 7.0 U2, we have the complete support for bare metal live migration when communicating with bare metal endpoints for Marvell adapters. And so another thing that we're looking at is more sort of generic ways of tracking access from I/O devices to host memory using I/O and MU-based dirty page tracking, but was not really a candidate when we started on this project. Next slide, please. So one of the motivating use cases for the bare metal support was the use of access to storage. And so when we're talking to customers for HPC type workloads, one problem is they want to use some kind of cluster file system that for the storage access. And also more long-term, when RDMA has achieved world domination, we just want to be able to provide any VM with RDMA access to shared storage. And so with this bare metal live migration support, at least in a virtual environment, I mean, we now have the opportunity to do so. And one example is the use of having a VM talking to a bare metal NVMe over Fabric target. And so we have a simple setup here where we have an initiator in a VM with PV-RDMA, and then we have a target which has also a VM, but with a PCI pass-through or direct path IO HCA communication, that it uses for communication for an SPDK-based NVMe over Fabric target. And in this case, the HCAs are NVIDIA Mellanox CX for 40 gigabyte cards. So in that case, well, comparing to TCP, I should say, we see significant performance improvements where previously the PV-RDMA had some issues with the kernel UOPs that were using DMA MRs. The performance, at least for this use case and for larger block sizes, is very competitive. Next slide, please. So just to conclude, I mean, we have presented the support for vendor neutral live migration of any VM, regardless of peer endpoints. This has been made possible with hardware support for suspend resume of queue pairs, RDMA namespaces, and dirty page tracking. It's been done with strong collaboration with our hardware partners, NVIDIA Mellanox and Marvell. And so I can see, so that concludes the talk, and I'll try to take a look at the questions for you.
Yep. So we have a question from Dwayne. Is there a plan to provide this RDMA vMotion support generically over OFI or libfabric? And has anyone considered whether the current libfabric API has support for the endpoint semantics such as suspend, resume, etc., that has been identified for IBQ pairs?
So I mean, we would like to make this a generic support. Currently, I mean, it's been the first release, and but moving forward, we would very much like to see this as a generic support.
Okay.
And
Dwayne, does that help? Or you have any follow-up questions? Okay.
I'll actually take myself off mute. Yeah, that's, I did want to say that, this work can definitely be applauded. This is not an easy problem to do over InfiniBand. And, but there's futures work that I think others would be interested in for supporting vMotion, more generically, like over libfabrics. And I think that, someone that's in this space should also be looking even more forward towards what it means to do vMotion in relation to CXL.
okay. Yeah, so for now, we've been focusing on Rocky only. This is what the PVRDMA currently supports.
No, I mean, I definitely see that what you have here, that you could take this as a baseline and fold in, at least for, verbs under libfabrics. And anyway.
All right. Well, thank you.
Thank you. Then there is a question from Jonas. With hardware support, why not use SRIOV instead of the PV?
PVRDMA? Or
We put the para-virtualization, right? It seems like that in your use case, you still use para-virtualization, even if you have support for suspend, resume, and all this in hardware. Why not go the full length, right?
so, well, so you would say, well, let's say SRIOV-based vMotion is something quite different, right? You have with SRIOV, I mean, if you're thinking about exposing a VF directly to the VM, then you would need to capture this. I mean, the VM would have a driver for that specific HCA, so that it can use the VF. Then if you want a vMotion, the device, I mean, it's kind of a complicated problem if you want to have this be vendor neutral. So in our case, we're isolated. I mean, you see the PVRDMA device inside the VM, but you can move from one vendor to another when you vMotion. As long as they support, of course, these APIs.
Right, right.
But if it's a virtual, I mean, if it's a physical device that you or the virtual function, you have all the device driver state, and that makes it difficult to have cross-vendor vMotion, or maybe, and even between different releases from the same vendor, or maybe even the same different firmware versions from the same vendor, you can have issues when moving from one system to another. So I think this is targeting the more sort of the generic use case where you, at some expense, I mean, obviously the paravirtual approach does add overhead compared to SRIOV. So this is a trade-off in terms of performance versus ease of administration.
Understood, makes sense. Thank you.
There is also a question from Don. What was TCP net link speeds used in comparison to Mellanox CX4? I think he had a more model number. Hold on, I'm scrolling up there.
So the
40 gig CX4.
So they use the same network. So both endpoints use the CX4s as the uplink. I mean, for both traffic, TCP traffic and the RDMA traffic. Should be.
Okay. Thank you. Here's another question from Dai. How is network routing changes done if VM move to a different subnet? Donglai, feel free to pipe up here if you need to have more context.
Yeah, I mean.
Yeah, I was thinking IP mostly is a static configured routing, right? So if the suspend and queue pair suspend and resume is locally decision, then how do you let globally know that one of the thread or whatever is moving and to a different network, part of a network? So at what point the network routing is changed on the different on the different switches in sub networks?
So.
Oh, that's not assuming IB.
Yeah, so for this is for Rocky only, right?
Okay.
So we just and we don't really. So the network traffic is just well, the Rocky traffic is handled like any other network traffic for this environment, so that you just the packets will just be routed to the when you do you hand off the VM from the source to the destination. There's an update of MAC addresses as well, so that the traffic will be routed to the new ESXi host.
No,
that's
okay.
similar.
I think
that's similar to how we
dynamic network protocol to deal with that.
So that's similar to how we deal with any network traffic for the VMs.
Okay.
All right, so we are 11 minutes over. I know I did not go through all the questions here, but please feel free the chat to keep going with the presenter here, Jorgen. And I would like to take this opportunity to thank Jorgen for being here, presenting with our OFA community. Thank you.
You're welcome. Thank you very much.